Chapter 1 has some material on the time value of money that you have to look at closely because there will be exam questions on time value money in a personal finance context. So I have prepared a handout that has, I think, 9 or 10 problems on it. You'll find it in the Chapter 1 folder. And there's also solutions in there in a PDF file for that same handout. It's up to you to sit down and go through this. You're going to need your textbook to do it. There's tables in the back of the chapter that you need to work with, or you could also work with Excel to get these answers. I'm going to go through these examples now, and what we're dealing with is both future value and present value calculations. The first batch of future value. Here's an example. Mary plans on buying land and building a house on it in 5 years. The type of house lots she would like to buy cost $150,000 today. If she assumes that real estate values will increase by 4% per year, what will the house lot cost her 5 years from now? So this is a classic example of the application of the time value of money. Let's take a look at the solution. Well, there's really two ways of doing this. You can use the tables in the back of Chapter 1, in the appendix of Chapter 1. You'll have to use the first table that has the future value interest factors in it, and you have to track down the correct factor. You looking at the interest rate that's assumed and the number of periods. Or you can use the FV function in Excel, the future value function in Excel. If you're a business major, and even if you're not, I would recommend the Excel way, although you're not going to be tested on that. I just think it would be good for you to sit down and try to solve some of these using Excel. The solution that I'm presenting shows the answers done both with the table and Excel. So here's the answer for this particular one. $182,550 is what that house lot will be worth in 5 years. This is assuming an annual interest rate or annual rate of return on that investment of 4%. And you can set it up this way, that the future value, FV, is equal to the present value times the FVIF, which is the future value interest factor, which you would have to dig out of the appendix for Chapter 1 over there on page 42. So you've got to make sure you're using the right table. This is the future value of a lump sum table. So therefore the future value is equal to $150,000, which is the present day value of that lot, times that future value interest factor for 5 periods and 4%. So if you look in that table on page 42, look at the intersection of 5 periods and 4%, you'll find a factor of 1.217. So you need to multiply that growth factor times the $150,000 present value to get the $182,550 value for the house lot. You can also do this in Excel, and I strongly recommend that you try that. If you do it, you have to use the FV function. And the FV function is set up by using some syntax, using a special syntax. And I've shown it here on this slide here. If you take a look at this slide, perhaps you want to print this out. And I will put the PowerPoint presentation also in the folder, so if you want to use this PowerPoint presentation, print out certain slides to help you solve these problems. But you can see in this one I use the function, and here's the syntax. The syntax is right down below here, below where it says where. So you see like cell C2 is the rate, and C3 is the number of periods, and C1 is the present value. So I would have set that up in, it looks like in a spreadsheet at the time, and certainly solve that. And there you have it right there. In fact, there's a slide that shows recently when I solved it, and it looks like in this case the rate was D7, the years were D8, and the present value was D6. I created that function right there that you see on the screen, and it gave me a number very similar to the one that I showed you a few moments ago. Now you can try any of these examples, problems, using the tables or solving them using either the FV function for future value or the PV function for present value. Let's try another one. What is the future value at the end of 6 years of an $800 investment that you make today, assuming that you can invest it at 8%? Now that would be at 8% per year. These interest rates are always quoted on an annual basis. So you'd use that same table. You'd go in there and you'd find this factor right here, a 1.587. Remember, this is going to be the intersection of the number of periods. And what is it in this case? It looks like, let me find it on my sheet here. Bear with me a second. It looks as though that would be the intersection of 6 years, 6 periods, and 8% interest. That factor of 1.587 from that same table in the back of your chapter that we used to solve the first problem. And so that $800, which you invest in year 1 and let it sit there for 5 years, will grow to $1,269.60. So that growth is all interest. If you do it in Excel, you're going to be very close. You'll be off by 10 cents. You should try that. The tables in the book are rounded. The figures are rounded there, so your Excel answer is actually more precise. So don't be alarmed if you're off by a few pennies or even a few bucks. It will be because of rounding. Here's a third example of future value. What is the future value at the end of 6 years of an $800,000 investment that you make today, assuming you can invest it at 8%, again that's 8% per year, with interest compounded semi-annually. So what that means is that the interest will be added to the account twice a year instead of once a year. So let's see how we solve this. In this case, you have to take a first step and adjust the rate. So the 8% becomes 4%. You divide it by 2 because of the semi-annual compounding. So every 6 months there'll be a 4% growth in this account because you take the 8% annual amount divided by 2. And the periods also have to be adjusted. This is for 6 years, but you have to adjust the periods to match up with the compounding frequency. So it will be 6 years times 2, which will be actually be 12 periods. So that's 12 half-year periods. $800 is the present value times 1.601, which is found at the intersection of 4% and 12 periods. That'll give you $1,280.08. And if you compare that to the previous question, question number 2, there's a bit more interest here because the interest is giving birth to more interest more frequently. So more frequent compounding every 6 months instead of 12 months. That alone will give you a greater future value. The Excel answer is slightly different. It's off by a few cents again. Excel, if you use the future value function, you'll get $1,280.83 for this one. Now the next one, number 4, is a little bit different because it's still future value, but it's the future value of an annuity. Make sure you know the definition of an annuity. It is equal cash flows per period for a set period of time. So a mortgage, for example, is paid every month for 30 years. That's an annuity. There's insurance annuities. People receive insurance settlements that pay them a certain amount per year or per month, and those settlements are called annuities. So know the definition of an annuity so you can recognize it when you see it. Try to recognize it in this description here. It says if you invest $2,000 a year for 10 years, see that? $2,000 a year for 10 years, that's an annuity. Specific period of time, a specific amount per period. Okay, so you invest $2,000 a year for 10 years. What will be the future value of the investment after the 10th year if you assume an annual rate of interest of 7%? And then what if the investing period was for 30 years? What would be the future value? I think I'm just going to do the first one with you. You can look at the solution that's online to check out the what if, the second scenario with the 30 years. Here you have to make sure you're using the correct table in the book. You've got to look for the future value of an annuity table. And so in the first scenario here, we have $2,000 times 13.816. That 13.816 is the future value interest factor for an annuity, okay, based on this problem. Now again, let me go back to the variables that were set here in this problem. It is $2,000 for 10 years at 7%. So this 13.816 is going to be found in your textbook in the annuity table in the back of the chapter. track that down. Make sure you're looking at the right table. And that right there is for 7% and 10 years. So that $2,000 that is deposited each year for 10 years grows to $27,632 by the end of the 10th year. Again, if you do it in Excel, you'll be off by 90 cents or something like that. It's still correct. In fact, Excel is more precise. Here's another one, present value of a future amount. So we're going to take a future amount and bring it back into today's dollars. And let's see how that works. Here's an example. You'd like to buy a home in 5 years. Your goal is to have $60,000 available for a down payment at that time. If you assume a 5% annual rate of return on your investment, how much do you need to invest today to have $60,000 available in 5 years? So you see, this one is working backwards. You're looking out into the future and you're saying, I need $60,000 as of a particular date. And I'm going to work backwards on this to figure out how much I need today. What's the present value of that? You know, what do I need to establish in an account, say right now, assuming I can earn a 5% rate of return, and that whatever that amount is, that X that we're looking for, will grow to $60,000 in 5 years. Present value of a future amount. So you have to use this basic formula here, that a present value is equal to a future value amount times a present value interest factor, and in this case for 5 years and 5%. So 5% annual rate and 5-year holding period. The PVIF, present value interest factor, for a lump sum can be found in the text in Exhibit 1-C. And I believe that is on page 44 in your textbook. Again, make sure you're looking at the present value factors that deal with a lump sum and not an annuity. That's a whole different animal. So you see we set it up down here. Present value is equal to $60,000, that future amount that we want to achieve, times 0.784. That's a discount factor. That's a present value factor that discounts the interest out of that future amount. It pulls the interest out of the future amount to give us a bare bones present day worth of $47,040. And you can prove this to yourself too. You can play with this and say, what if I took $47,040 and invested it today at 5% interest and held it for 5 years? It will grow to $60,000. You can prove that to yourself. But anyway, this is what you would have to invest right now and keep it invested for 5 years at 5%, and then you'd have the $60,000 that you need for the down payment. This can also be done in Excel with the PV function. You'll get an answer that's off by a few dollars, but actually the Excel number is the correct one. And on the exam, if this comes up on the exam, you can just use the tables. I will accept both answers, the table or the Excel version, whatever you're comfortable with. A lot of students just like to use the tables, but I really think for a practical matter, you should get into the habit of using Excel. You're going to use it in the real world a lot. And that apparently is the end of the slideshow. I went as far as the 5th problem. You can go through, and the rest of it has several other items in there that goes all the way up through a 9th problem where you're asked to do a loan amortization table. You should try all of those, and good luck.